Hello everyone, welcome to Dakshana E classroom program. So in the last lecture we discussed about LC oscillation in the last part. We saw actually in LC oscillation both inductor and capacitor are energy storing device. So nowhere energy is actually getting dissipated. So if we are supplying the energy to the circuit in either way, whether it's initially supplied to inductor or maybe capacitor, so when it is like switch is on, then energy keep on oscillating between electric and magnetic field, and we saw how like charge and current keep on like we are getting as sinusoidal functions. So and we calculated the kinetic energy in electric field and magnetic field at any moment of time. So we can see some of the application based on that. So let's see some problem. So here we have one simple case. Actually in the figure shown, initial charge on the capacitor is 200 microcoulomb. So let's see. So initially means Q0 is given as 200 microcoulomb charge. Find the instant when the energy stored in inductor become 1/3 of the energy stored in capacitor. So we know actually energy in capacitor is Q square by 2C. Energy in inductor L is half Li square. And we know total energy is equal to energy stored in capacitor means electric field plus inductor means magnetic field. So I can write it capacitor plus inductor, and this is Q0 square by 2C. Is it? So now it's saying something actually. The instant when energy stored in inductor become 1/3, so means I can write U L is equal to UC by 3, and UC I can write at some moment of time is, let's say charge become Q, then Q square by 2C. So if I substitute these things here, this implies UC is, this is Q square by 2C plus UL is equal to what? 1/3 of UC, that is Q square by 2C. And this is Q0 is the initial charge divided by 2C. Now if I simplify this, it's coming out to be basically like 4 Q square by 3 into 2C, and this is Q0 square by 2C. 2C gets cancelled and we are getting actually Q is equal to root 3 by 2 Q0. So it is the instant when charge reduces to this way, this one, at that moment of time energy stored in inductor will be 1/3 of the energy stored in capacitor. And we know actually if energy initially the charge is only on the capacitor, then we can write Q as function of time is equal to what? Q is equal to Q0, that is Q0 into cos of omega into t. And omega will be equal to what? Omega we know it's 1 by under root LC, and if we have 2 microcoulomb and 0.2, so we are getting actually omega is coming out to be, here it's 1 by under root 2 into 10 raised to power minus 6 into 2 into 10 raised to power minus 2. So it will be 1 by 2 and 10 raised to power, so it comes out to be 1 by 2 into 10 raised to power 4. Is it? That is your omega. So now I can like substitute here. So this implies this is root 3 Q0 by 2 is equal to Q0 into cos of omega t. So this cancel. This implies omega t is equal to how much? Omega t cos theta is equal to root 3 by 2. That root 3 by 2 means what? It's basically 30 degree. So 30 degree means it's pi by 6, and this implies t is equal to pi by 6 into omega. Omega you can write into 2 divided by 10 raised to power 4 second. So the answer comes t is equal to pi by 3 into 10 raised to power minus 4 second is the answer. I hope you understood. This is the system given. It's mentioned initially there is total charge only on the capacitor, means no energy is there in inductor. The charge as function of time can be expressed this way by simply from this where Q0 is actually 200 microcoulomb. L is given, C is given, we can getting directly omega 1 by under root LC. Solving, we are getting this. Condition given, find the instant when energy stored in inductor become 1/3. Energy stored in capacitor plus inductor is total energy. This energy become 1/3 of this. So this energy and UL is 1/3 of this energy. Solving, we are getting value of Q, and simplifying, we are getting the time when this will happen. So we can see this is one simple application of LC oscillator. We have another problem here. So initial charge on the capacitor. So again here I can write Q naught is equal to what? 100 microcoulomb, and I can write charge Q. Let me first get omega also. So omega will be here what? 1 by under root LC. That is 1 by L is 6 into 10 raised to power minus 3 into 5 into 10 raised to power minus 6, right? And this implies 1 by under root, this is 5 into 6, so it will be like 3 into 10 raised to power minus 8, and this is 1 by root 3 into 10 raised to power 4. This is per second your omega. So we are getting here omega. Then I can write Q as function of time is Q naught into cos of omega t. Where I am having Q naught, I am having omega also. Alright, so now what it is asking, find the current in the circuit when charge on capacitor reduces to 50. So initially it's this, so means it is becoming Q naught by 2, is it? So I can get that when charge reduces to 50 microcoulomb, this implies 50 microcoulomb, 100 microcoulomb into cos of omega t. This implies omega t is equal to pi by 3. This is what? 1 by 2, omega t is equal to pi by 2. So this, we are getting this, and it is asking about the find the current. So current is what? I can write I is equal to I naught into sine of omega t. And what is I naught? I naught is the maximum current, and that is omega into Q naught. So omega I got this, and Q naught is 100. So I can write this is omega is 1 by root 3 10 raised to power 4 into this is 100 10 raised to power minus 6. So I naught is coming out to be, this is 10 raised to power like 661 by root 3 ampere. We got maximum current, and current when this, so I is equal to 1 by root 3 into cosine omega t, and omega t is pi by 6, pi by 3. Pi by 3 means it's root 3 by 2, so it's coming out to be 1 by 2 ampere. So maximum current, this, the current in the inductor when charge become this much is, we got the omega t value. Substituting here, omega t is this, and like here we are getting the current is half ampere. So these are like simple application of LC oscillator. Let's see some more problems. Okay, so see next problem also based on LC oscillator. So we have, this is the circuit diagram given. Initially 900 microfarad capacitor, this is charged to 100 volt. So initially this is charged to 100 volt, and 100 microfarad capacitor, this is uncharged. Then switch S1 is closed for T1. So when this is closed for T1 time, then this will be like, you can see it is open, so this will act like LC oscillator. So this is open, like closed for T1 time, after which it is open, this is open, and at same instant switch S2 is closed, this is open, and then same instant this is closed. So then after that, what will happen, actually this circuit will act like LC oscillator. Initially this was active like LC oscillator. It is now found that 100 microfarad capacitor is charged to 300 volt. So finally this is charged to 300 volt. Now you are asked to find the minimum possible values of interval T1 and T2. So T1, T2 values are like we need to find. Okay, so let's solve it. So let me first check the energy, how much energy has been transferred to this inductor. So energy like that capacitor, so energy on 900 microfarad capacitor initially, this I can write U 900 is equal to half CV square, that is 1 by 2 C 900 microfarad into V square, 100 into 100, 2 4 6 zeros, 6 gone, so it's coming out to be 4.5 joule. Right, this is the energy means stored in this capacitor initially. Finally, the energy transferred to 100 microfarad capacitor. So how much that energy? So energy to 100 microfarad is 1 by 2 into again C, this is 100 microfarad into V square, that is 300 into 300, and we are getting, actually it is also coming out to be 4.5 joule U 100 microfarad, U 100 microfarad, 4.5 joule. What did it mean? This means like complete energy is getting transferred to 100 microfarad. And next point is that if initially total energy is on, let's say initially total energy is here, then how much time it will take to transfer it completely to here, is it? So we know the total time is T is 2 pi by omega. The time taken, minimum time to transfer complete energy from electrical to magnetic energy is T by 4. So minimum time to transfer complete energy from capacitor to inductor is T by 4. So means what is happening? Initially this circuit must be switched on for T1 is equal to T by 4. So it has time period T1 and this circuit will have time period T2. Then this T1 I can write should be equal to capital T1 by 4. By that time this complete energy will be transferred to this inductor. After that inductor will have initial energy and this is open, so it is simply broken out, taken out, separated out. Now this will act like one LC oscillator. Here time period will be T2, and then to transfer complete energy from here to there, again the time period T2. So this time switched on for T2 should be equal to time period by 4. So the answer is the minimum values of T1 and T2 is T2 by 4 and T1 by 4, and we need to find T1 and capital T2. Is it? So here I can write T1 is equal to what? This is equal to T1 is 2 pi by omega, right? And omega is under root LC. So LC, I will write this is, let's say, C1 L C2. So this I can write L C1, and this is 2 pi under root L is how much? L is 10 Henry multiplied by C1 is 900 microfarad into 10 to the power minus 6. Okay, and similarly T2 is coming out to be 2 pi under root L C2. This is 2 pi under root L into C2 100 microfarad. Solving this, we are getting it comes out to be 0.6 second, and this comes out to be 0.2 second. So we got this is capital T1, this is capital T2. Is it? So now I can write, it's asking the minimum possible values of interval T1 and T2. So what should be the small t1? That is, small t1 should be capital T1 by 4. small t2 should be capital T2 by 4, because you can imagine initially this is the active circuit, total energy here, this time to transfer complete energy from here to there will be the time period of this LC oscillator, that is T1 by 4. So here I can write the minimum possible time interval, the minimum possible time interval so T1 is equal to capital T1 by 4, 0.6 by 4, that is 0.15 second. T2 is capital T2 by 4, that is 0.2 by 4, 0.05 second. So these are answers. So I hope you understood. So this way we can approach for problem based on LC oscillation. I think you should not have much problem in this. You try as many as problem you can based on this topic. You will feel more confident. So let's continue with the next topic. Okay, so the next topic is eddy current. What is eddy current? It's just a small topic. Let's try to understand that. So in this situation, first thing is we have seen whenever some conductor is passing through a magnetic field, or when conductor cuts the magnetic field lines, or if flux linked to a conductor is changing, some EMF is induced in the conductor. And what that EMF does actually, if there is some path, there is some possibility of flowing current, then I can say that EMF will result in some current in the conductor. So here we have some special situation. So let's consider this region has some magnetic field. This is the region having magnetic field, and I am, let's say, suspending one conductor. So one conductor is suspended here with this. So this is one conductor, let's say like this, and I'm releasing it, so it's like oscillating this way. What will happen in when this conductor is entering this magnetic field, flux linked to this conductor will keep on changing, is it? So let's say after some time it will be here, then when it is like about to enter, you can see the flux through this is changing. Flux is changing, that will result in some EMF in the conductor, and it's like conducting plate, so there is a scope of flowing current. So in this case, some current flow in some circular loops depending on how EMF. So current flow in circular loops, and this current is called eddy currents. Normally what happens when conductor is there, like the resistance of these conductors is low, EMF produced is quite good, so the current produced in these conductors is of good magnitude or large magnitude. And this conductor current or current in this conductor in the terms or in the form of loop result in loss of electrical energy in the form of heat. So I can define here actually eddy current when a changing magnetic flux is applied, you can say, or linked to a conductor, or I can say thick or bulk conductor material, conductor that result in circular currents in the conductor. These circular currents are called eddy current. So I hope this is clear. So here, when conductor is moving in a magnetic field, changing flux is linked to, there is maybe like another possibility. Either way, whenever there is some changing flux linked to a conductor or bulk conductor, lot of EMF is produced, and that EMF result in some circular loops or currents flowing in some circular loops, and these circular loops, current flowing in these circular loops is termed as eddy current. So here you can see, as conductor have small resistance, that result in large eddy current. Eddy currents, and these eddy currents leads to loss of electrical energy in the form of heat. So if we want this eddy current to be like reduced, then what can be done? So to reduce, either we can laminate these like conducting sheets, or sometime if we are able to reduce this area, is it, then like loop size will be reduced. So this can be done, is it? So to reduce the eddy current, reducing eddy currents means reducing the loss. Sometime we cut some strips are cut out from conductor. Like if I say this is one conductor, so this is one possibility of conductor, and to reduce it eddy current, what I'm doing is I'm cutting these strips through this conductor. Like this. So these strips will not allow current in large loops, and that will result in small current, and that way we can reduce the eddy's losses. Or either we can, like if we are having like thick conducting material, then we can laminate two sheets, is it, that happen in case of transformer. So laminating conducting sheets also reduces eddy current. So I hope it's clear. This is like eddy's current. We have some application of eddy's current. Let me write those applications of eddy currents. There are actually many applications of eddy currents. Here I am mentioning two. One more point here, eddy current also called Foucault current. So application is, one is in electrical braking, another is induction furnace. So first thing is like eddy current, whenever some changing magnetic flux is there, current is induced that result in heat. If rapidly changing magnetic field is applied and large conductor is there, then heat produced will be very high, and that heat produced sometime even result in melting of metal piece placed in rapidly changing. So that way it is also sometimes used in induction furnace and electrical braking. So the high speed trains or bullet trains, actually you might be knowing, they are also called maglev technology, magnetic levitation. In that situation, actually the train is not touching, not running on the rails, they are actually in the air when it is running at very high speed. So like wheels are not touching anything actually. So magnetic levitation is there, it's lifted like upward. Now what happened actually, if we want to stop this train, then how we can, because wheels are not even touching, so there is no possibility of applying brake. for that system actually we have like these eddy currents, and these create some brakes. So what is happening, some wheels are there, those wheels when we want to like stop the train are passing through changing magnetic field or electromagnetic, that is creating magnetic field. So when they are passing through that, then it's changing, flux is linked, eddy current is produced, and this eddy current is opposing the motion, and that actually apply brake on the magnet trains, and that is how electrical braking system also work based on eddy current. So this is all about eddy current. You read about it from some like NCRT book also, you may find some points. So I hope you like clear with this eddy current. Let's see the next part. Okay, so the next topic is transformer. It's like quite interesting thing here. So first let me tell you how exactly transformer work and what exactly is transformer. So if we look at the construction of transformer, then it has basically one iron core, like seats are there, and they are laminated. Why we are not using complete one like thick iron core is because of to reduce eddy losses, eddy current losses. We just recently saw eddy current. So if what will happen, like thick iron core is there, then lot of eddy current losses will be there, and it can be so much high that it can even melt this actually. So to reduce that, we are cutting into slabs and cutting into laminated sheets, and they are laminated actually. So like iron core is basically made of thin sheets, and they are laminated so that eddy current losses can be reduced. So this is iron core. And what is that? Now we have like windings. Okay, so wire, copper wire normally is wrapped around, wounded. So there is one primary coil and this is another secondary coil. They are connected magnetically, they are not connected electrically. These two like windings are not electrically connected. There is no direct connection of these two coils. Now what is happening actually, when some AC input is given to this AC input will result in some changing magnetic flux in this coil. We call this as primary coil. Np is the number of turns in primary coil, Ip is the current in the primary coil, velocity, potential drop, this is the potential difference across the primary coil, and here I will write even these terms individually. Okay, so here what is happening, just try to understand this. When AC input is given, this input is AC, so means it will be fluctuating, and that will result in some fluctuating or varying magnetic flux through this. Now we want this flux to be linked to this. Then what can be done actually, even when they are like coupled like this actually in between, then also like the flux changes, depends like how much I can say the magnetic mutual inductance basically changes. In this situation also there is like, because the flux is inside this core, so almost all flux is linked to this coil. Now what is happening, this is the secondary coil. So in secondary coil we are having coil and some changing flux, because this flux completely passes here. So when some changing flux is like linked to this, then what will happen, this coil will induce some EMF. So that way in this coil some EMF is induced, and this EMF we are using here for load. Now based on the number of turns in these coils, the potential difference or the EMF of this input or EMF, it can be increased here, output EMF, or it can be decreased, depending on, if that depends on number of turns. I will tell you how exactly also. So if number of turns in secondary coil is more than number of turns in primary coil, then EMF induced here will be more than EMF here, and vice versa. If number of turns in primary coil is more than number of turns in secondary coil, then EMF here will be smaller. This work based on still power conservation or energy conditioning. It is not in like generating power or like understanding, not like destroying also. Yes, some losses are there, so there you can consider it's like dissipating some power, but actually there is conservation of energy here also. So now what is happening, basically this input power, and here we are getting output power. So it like when some current is there, so in this situation, if it is increasing the EMF, then it reduces the current actually, and vice versa. If it is decreasing the EMF potential difference, then it increases the current. So it's changing potential drop and current. This actually increases potential difference or decreases potential difference. So transformer, we define it is a device which raises or lower the voltage in AC circuit by mutual inductance. I hope you understand. And this is the construction of this transformer. So here, like different terms are there I am writing. So like how exactly what is happening here, that should be clear to you. So this system, this device, we call it as transformer. It work based on mutual inductance. So here this is a iron core, changing flux here linked to secondary coil, and that generate EMF in the so here I can write changing magnetic flux in primary coil is linked to secondary coil by iron core. And that way, when this changing flux linked to secondary coil, it will generate some EMF in this. Some properties of this, it work because if listen it, if constant EMF is here, then what will happen? No changing flux will be linked to this, and then there will be no EMF induced in this circuit or in secondary circuit. So that's why it work only on AC supplies, not for DC supply. It can increase or decrease either voltage or current, but not both of them simultaneously. If it is increasing the voltage, then definitely it will reduce the current, so that power or energy remain conserved because it's not generating energy. It does not change frequency of input AC, and no electrical, I told already, in connection between the windings linked between primary and secondary. So these two windings are only connected magnetically, not electrically effective. So because not connection is, no direct connection is there, so we can definitely say no current is passing directly. So that means like the resistance, ideally, like if we look at effective resistance between primary and secondary windings, then it will be like almost infinite or very high. One more thing here, actually, we are assuming ideally, is it? You can write ideally, we assume that there is no loss. There is no loss. Then you can write this flux per turn in each coil will be same. So flux per turn in primary will be, because same number of field lines will be linked to here. So that's why I can say the flux per turn in secondary and primary coils will be same. So here this NP is the number of turns, total number of turns in primary coil, and similarly I can write N as number of turns in secondary, V as VP input voltage or EMF in primary coil. Similarly, V as input, you can write output EMF in secondary coil. I think you can easily understand this. IS current in primary and secondary. P is the power in primary and secondary coil, and I am writing here E as EP, and ES is the EMF induced in primary and secondary. So these are some symbols which will be like used. Let me tell you how these things are related and how it actually increases EMF or increases potential difference by decreasing current. So that actually happened with the like flux. So let me just erase this part. Okay, so here the point here is that flux linked per turn is same in both coils, primary and secondary. Flux linked per turn, so phi primary always equal to phi secondary. Now there are NP number of turns, so I can write EMF primary will be equal to minus of NP into d phi, because total flux will be what? Phi net in primary will be NP into phi P. Similarly, phi net in secondary will be NS into phi secondary. So I can write EMF in primary will be equal to what? D phi net divided by dt minus, and that will be equal to, I can write NP into d phi p by dt, or because these are equal, so I can write it simply phi, and this is minus NP into d phi by dt. Similarly, EMF in secondary circuit coil, it's minus of d phi net in secondary divided by dt minus ns d phi s by dt. That can be also minus n secondary into d phi by dt. Is it? So this is the induced EMF, and I am writing if there is no loss of power or anything, in that case what I can write, this induced EMF in primary is also equal to the applied primary voltage, and similarly induced EMF in secondary will be equal to voltage in secondary. Now here, because we have already considered, there is, like, I'm assuming here that there is no loss of power, that implies assuming no loss in transformer. Ideally, actually the efficiency is not 100%. Practically, if we look practically the efficiency is not 100%, it's from like 70 to 90%. But yes, for the ideal calculation I am assuming that there is no loss, so it's like 100% efficient. In that situation, I can write power in primary will be equal to what? E primary into I primary, and similarly power in secondary will be E secondary into, this is I secondary. Is it? So this implies if no loss, then power should be same, and that implies E P I primary should be E secondary I secondary, and this implies E primary by E secondary is equal to I secondary by I primary. And from here, if I divide E primary by E secondary, so you can say d phi by dt will be simply getting cancelled out. This is ratio is coming out to be number of turns in primary, so this is equal to number of turns in primary, number of turns in secondary. So this way, this is called transformer like turn ratio. It's also called some constant K and called turn ratio, number of turns ratio. So this way you can say if like number of primary NP, is it? So there are two possibilities here. One is step up transformer. It actually increases the voltage, increases the output voltage. Here output voltage, you can write EMF is high, so output means secondary. So in this situation you can write N secondary must be higher than N primary. So number of turns in secondary circuit must be higher than number of turns in primary. Similarly, that will be called your step. So in this situation, E secondary will be higher than E primary, and I secondary will be less than I primary. Power input will be still same, number of turns we already got, and power is still same. Current, yes, we got the relation. Second, like next part is the step down transformer. Let me write this little bit. So first thing, I actually like, this is one of the like setup of transformer. Just because we can't in circuit, if we are using like writing transformer every time, it's not possible to draw it this way. So just like resistor, inductor and all those electrical appliances circuits are there, we are using some symbol for them, right, to write down in some circuits. So exactly there is one like notation symbol. Let me erase this part. for transformer also. So how we write, how we actually, so transformer, first thing is, it is like drawn, this is primary coil and here secondary, sometime even this is complete called transformer. That is how we draw a transformer. So here it's a NP and secondary this way. In this situation actually, so step up transformer, basically you can say this is the step up transformer, step down transformer, this is symbol of transformer, and here I have drawn step up transformer also. Similarly second will be step down transformer. So that will be like here number of turns in primary coil will be higher than number of turns in secondary coil. So this is an primary and secondary. You can see number of turns in primary is more than number of turns in secondary. So here the output voltage will be smaller than, so this is a step down transformer. So in this situation, E secondary will be less than E primary, and definitely I secondary will be greater than I primary, and N secondary will be less than N primary. So that is called your step down transformer. I hope this is clear. So that this way you must be now understanding how it actually increases the voltage and how it decreases. These are used a lot because you must be seeing that the power that like comes to our village or to our nearby station, it's like in thousands or sometimes eight, like 1100, is it even like higher voltage, but the power or voltage that we are using in our homes, it's only 220 voltage. So how that basically 11,000 or even higher get converted into 220, and you might have seen definitely some transformers kept in the nearby areas. These are exactly working this way. So they convert the like input or power supply to the required home appliance voltage. So that is the function of step up, like step down transformer. Similarly step up transformers are placed at the power stations, like power generators, where like power is electrical power is generated. Now next question might be wondering that why we are doing this, why we are first increasing the voltage then decreasing the like voltage at the like at source we are increasing the voltage, and at the exactly like end point where power is actually used we are decreasing. Why we are doing, what is the point, why we can't simply transfer the volt like power at whatever it is being generated? And there is some issue, there is benefit, there is some profit in doing this. So the point is that if we are transferring the power at low voltage, that means current will be higher. Current is higher, you can see the power lines, power comes from many, even thousands of kilometers, so the resistance of this power line will be very high. Getting it? In high current and high resistance, then the power losses in transmission will be I square R, very high, it can even sometimes melt the wire cable also. But if we are increasing the voltage and reducing the current, that way voltage difference increases but the current reduces, the losses in the power lines, transmission lines will be I square R. So I square become very less, then this overall loss become reduces by like many factors. So this way it is necessary, it is must to use transformer and step up the power at the generator and step it down at the source or like final destination. So I hope you understand why transformers are important, why it is required. Okay, so I was talking about here, so ideally we can say efficiency of the transformer is 100%, but practically efficiency CNC is around 70 to 90%. So in this case, how we define actually efficiency? So in transformer, we can write P output is equal to this. You can write I secondary into V secondary, and P input you can write I primary into V primary. So this is the power supplied. This is the power we are getting output. Then efficiency is defined as power output divided by power input, and this is I secondary V secondary divided by I primary into V primary multiplied by 100, then you will get in percentage. So that way we can define efficiency of transformer. I hope by this time you are clear with the transformer, that what is actually a transformer, how it work, based on what principle. That is basically based on mutual inductance. Two coils are coupled magnetically, and one change in flux in one coil is linked to another coil, and that result in EMF. So you can see number of field lines, they are limited to only this iron core. Number of field lines in this will be exactly passes to number of field lines in this. So that's why I can say the flux per turn will be same in both primary and secondary coil. But when we are changing the number of turns, then the EMF in primary and secondary can be changed, and that comes on the like cost of changing current also. So if EMF in the secondary is increasing, by default the current in secondary must be lower. So this way actually the transformer is, it can be increasing the voltage, can be decreasing the voltage. It has like lot of application. Without this it's like next to impossible to get power at like far places, like because otherwise losses will be very high. So this is all about, and you can do some calculations, you can solve some problem there, like if input voltage, power and number of turns, so on. And this is all about transformer. Wait. Okay, so there is one more thing actually that is about transformer, that is losses in the transformer. So as I mentioned that ideally we consider 100% efficiency, that there is no loss in the transformer, but practically the efficiency is only up to 70 to 90%. So some energy is getting lost in the transformer also. Where and how it's getting lost, based on that we are like categorizing and all the losses in different forms. So one is called losses in transformer is copper loss. So I told actually primary and secondary windings are made of copper. Current passes through these windings, and we know the copper also ideally doesn't have zero resistance. So the current is passing through these copper windings. Then what will happen, if R is the resistance of each copper winding, then I square into R will be the loss of power or energy in the form of heat. So this loss in the form, like loss in copper winding due to having some resistance, we call that copper losses. When current flow through the transformer winding, some power is wasted in the form of heat, and that is given by heat is the I square into R. To what we can do for this, to minimize this, we can use a thick copper windings, that then resistance will be reduced, and we can this way reduce the loss. We are not in position to remove it completely. Another is eddy current loss that I already just told. So eddy current you must have understood. Here copper like iron core is there. So if we are, let's suppose, not using sheets of iron core, we are using complete thick metal iron core. In that case, the change in flux linked to this iron core, is it? This here you must be remembering this iron core we used. Let's suppose here we used this seeds. Instead of that, if I am using complete one iron core, then you can see the thickness. This is very high. Changing flux is linked, and a lot of eddy currents will be there. So this loss is called eddy currents. Even when we are using some strips or sheets of like iron, then also some still eddy current flux, eddy current losses or eddy current is there. So we can reduce this by only like instead of using thick iron core, we can use strips, and they are laminated, so the flux is not basically connected in each other, like they are not connected electrically. This way the eddy current losses can be reduced. Is it? So instead of using this thick, we use actually some strips, like very thin strips actually are used. So this way. And next is stresses loss. See, here what is happening? Changing magnetic flux. So with current or EMF in this here like is AC alternating, so it will be increasing, decreasing, increasing, decreasing, so on. So what is happening? This iron core is magnetized, demagnetized, magnetized, demagnetized. This case, the loss, it's like if we plot its magnetized field or magnetism, then this graph looks like this, and here you must have seen this in magnetism, that area under this graph gives you the loss, and that is also in the form of heat. So this loss we call stresses loss, and if we want to reduce this loss, there is no option. What we can do is we can choose a material whose this area under this graph is smaller. In that case, the loss or stresses loss can be reduced. And the last one is magnetic flux leakage. I told actually here that magnetic flux in primary and secondary number of flux per turn is same or must be same, but ideally it is not same, is it? So some flux actually get lost of magnetic field maybe this way, and they say they are not completely linked to this. So in this situation, some energy is getting lost by in the form of flux leakage. So magnetic flux produced in primary winding is not completely linked to secondary winding. This is all about basically transformer, what it is exactly, how it works, and losses in transformer. Okay, so ideally your chapter almost finished here, and here generators and motors are left, but these are simple, it's small like things. So you read the theory from any book actually available, NCERT also you will find actually. So working principle you must have already. So when a current carrying like winding is there, current carrying like some coil is there, if it is placed in magnetic field, it experiences torque. So in case of generator, what we do, we provide external mechanical torque, rotate it, and changing flux will induce EMF. That is the principle of generator. In case of motor, we apply, what we do, we provide electrical energy. Is it so? Electrical energy is provided, that will generate torque. Flux will be changed, and that will generate torque, and that is how your motor works. So read about it, and hopefully this is all about EMI. You solve more problems based on it, and let's see you in the next class with new chapter, new topic. Thank you so much.